Hi, in this video we're going to learn about exponential graphs. And they are graphs that have the very basic form y equals a number, to the power of x. Now, this base number could be a variety of different things, and the different things actually will change the graph. So let's have a look at a couple of different graphs for different values of a. Okay, so here up the side, this column, you can see all the different functions that I want to show you. We're going to start with the first one, f of x equals 2 to the power of x. So we'll turn that on, and here's the general form. So you can see as numbers get, the x values get lower and lower, our y value is very approaches 0. And this is because 2 to the power of, say, negative 2 means 1 divided by 2 squared. In other words, let me just quickly write this down. When x is negative 2, we have 2 to the power of negative 2, which of course is 1 over 2 squared, which equals 1 over 4. And say if we have now x is smaller again, say negative 3, then 2 to the power of negative 30 is 1 over 2 cubed, which is 1 over 8. And 1 over 8 is smaller than 1 over 4. So that is why we see this behavior, and it's going to be an asymptote here at y equals 0, because it'll get closer and closer to y equals 0 but never touching it. Now another feature is it goes through 1 here, y-intercept of 1. That's because when x is 0, it's going to be 2 to the power of 0, and that's always 1. Then it gets larger and larger and larger, because obviously 2 squared, so 2 to the power of 2 to the power of 2 is 4 there. And then, 2 cubed, when x is 3, it's 2 to the power of 3, and if we go up, that would be 8. There we go, at 8. And so on and so forth. So that's pretty expected. Now we can turn that one off and have a look at 3 to the power of x. And you can see basically the exact same basic shape going on here. Once again, it cuts through 1 due to that index law, and it goes along there. So you can see this graph is a bit steeper. Let me turn that last one on again. So this 3x graph, which I'm flashing for you here, it's a lot steeper up here, and it also cuts into this into the asymptote a lot quicker. So now put on the graph of 4x, leaving the others up. So once again, it cuts in even quicker and it rises much quicker again. Now, let's look at what happens if a, our base number, is a fraction. So it's between 0 and 1. Here, if a is a half, so half to the power x, it looks like this. Now, this is because if we have a half to the power 2, that is a quarter. If we have a half to the power 3, that's a half times a half times a half. So it's getting smaller, it's halving every time. That's actually 1/8. And then down here, 1/16. So it's getting smaller and smaller, and so the asymptote's still y equals 0, but it's going in the other direction. And here, it's basically the opposite thing happening. When x is negative 2, that's like a half to the power negative 2, which then becomes 2 squared. So that will be 4. 4 here for negative 2. And that's what we see. And then we can put on a third, and we'll get a similar thing going on, and a quarter, a similar thing happening there as well. But once again, it's going steeper. So if we only have a half to the power x and 2x, you see that these are sort of reflections of each other across the y-axis. And similarly, if we have 3x and a third x, those are also reflections of each other. Okay, so we've covered the case where the base number a is greater than 1, and we've covered the case where it's a fraction, where it's less than 1, but greater than 0. We haven't covered what happens when it's actually exactly equal to 1, so 1 to the power of x. And here's what it looks like. The graph's just always 1, always 1. And that makes sense, because no matter what how many times you multiply 1 together, it still equals 1. then what happens when the base number is 0? 0 to the power x. Well, you can sort of see it there. It's just along this x-axis because 0 to the power of anything is always going to be 0. So that's going to happen there. So let's summarize some of our knowledge. Let me get rid of this for a moment. So when a is greater than 1, we have a graph that looks like this. And we've got an asymptote here. So that's an asymptote. And the equation of the asymptote is y equals 0. And it cuts through here at this point, which is 1. Cuts through at 1. Now, if however a is between 0 and 1, our graph is reflected. So this point here is still 1. There's still an asymptote along here. So that asymptote is the same with the same equation. It's just reflected. So this is if a is like a fraction. Now we have if a is 1, well then it's 1 to the power x. That's sort of this basic one where it's just a straight line. Whoops, that straight line was not straight. Straight line. Hopefully you understand what I'm trying to get at there. X. And if we have a equals to 0, then it's even more basic. Y. Then it's just a straight line as well. The only thing to mention about a to the power 0 is that'll be of this form, 0 to the power x. Now what happens when x is negative here? If x is negative, then we can write this as y equals 1 over 0 to the power x. But you can't have, this bit here will be 0, and you cannot have a division by 0. Division by 0 is not allowed. No dividing by 0. By 0. So, in fact, this case here, when a is equal to 0, is only valid in this region. So a equals to 0 is only valid for the domain where x is within 0 to positive infinity. Or in other words, r plus, but also, I guess, the union with 0, because 0 is allowed as well. There we go. So that's that case there. It's only this bit that is allowed. This bit not allowed. Okay. Now the curious among you probably wondering we've covered almost the whole real domain here, but we have not covered the case where a is less than 0. In other words, when a is negative. And here's the reason why. If a is negative, then it's possible, I'll explain it using an example. So let's say that a is negative 2. Then we could have y equals negative 2 to the power x. Then what happens, imagine if x equaled a half. Because that'll happen on our graph somewhere, like here's 1, and 1 we would expect it to be fine, that would just equal negative 2 down here somewhere. Negative 2, and you're like, yep, it's looking fine so far. But then when x is a half here, then our equation is y equals negative 2 to the power of a half, which you know is the square root of negative 2. Now in this course, Year 11 methods, we cannot have the square root of negative numbers. It is not allowed. And so this is not allowed. And we're going to be having that in this sort of whole region, and we're also going to be having it, so 2 is fine, but then between 1 and 2 we've got fractions happening again, improper fractions and stuff, so it's not allowed in there as well, and so on and so forth. So that case is not allowed. A cannot be negative. Now in other courses, and for the curious among you, you can sort of look it up, what happens. So here I've got it on Wolfram Alpha online, and here you can see that they've got real parts in blue and imaginary parts going on at once with this wavy sort of nature. Or if you're curious, you could try plotting on a CAS calculator and end up with this chaotic looking thing. But we're not going to go into that in this particular course because it's off the course, as I mentioned. Now, in this next part of the video, I'm going to explain that I'm going to talk all about reflections and translations and dilations. And then finally, we're going to have a look at some examples. So first, let's look at reflections. We'll look at reflections first. So firstly, we can have a reflection in the a reflection across the x-axis. So if we look at a case that might look like this, y equals negative a to the power x. So let's have a look at that reflection. Okay, so let's get up our f of x equals 2x standard graph. And now here I'll do a reflection. So I'll just put a negative sign in the front. And there we go. It's been reflected across the x-axis there, just as you might expect. And we can do the exact same thing using our fractional graph. So here we've got p of x is half to the power x. So here it is, just as you remember. And putting a negative sign out the front reflects it across the x-axis like that. So perhaps for the rest of the video, I'm going to assume, just for simplicity's sake, that a is larger than 1. So in other words, we're always going to start with the standard form going up like that. I'll put in some axes too. There we go. So we're going to start assuming that where our base graph is this graph. So now this type of reflection here is going to push it like that. And now we have a second type of reflection, that's across the x-axis. And now we've got a type across the y-axis, which is when the negative sign is just before the x like this. And I imagine you know exactly what's going to happen here. It's going to be reflected in the other direction. So here's the standard one, and it's now going to be reflected going the other way. So let's have a look. So we'll start with our 2 to the power x graph, and now I'm 2 to the power of minus x. There we go, it's just been reflected across. So notice that it still goes through this key point here of 1. So there's reflections. We've got our reflection across the x-axis, which brings it this way. And we've got our reflection across the y-axis, which sort of swaps it around that way. Or you can put the arrows the other way if you want to. There you go, you get the idea. Okay, so next up, translations. Translations. Okay, so here we could have y equals ax plus h, and this is going to shift it upwards h units, and it's going to shift the asymptote. So let's have a look at, here we go, here's our trusty 2 to the power x graph, and next we've got 2 to the x plus 3. Put it on, and you notice the asymptote, instead of being y equals 0, is up at 3. And notice this key point, instead of going through at 1, now goes up through at 4. And 4, of course, is our 3 plus our 1. So it's all just been shifted upwards 4 units. Okay, so that's our vertical translation. And our horizontal translation is if we have y equals a x minus k, means it's going towards the right, k units. So let's take a look at an example of that. So here's our 2 to the power x. Now here we've got 2 to the power x minus 4. So if we put on this one with the minus 4 there for k, so k is 4, it's been shifted across 4 units. And you can tell because of this key point here, where it used to go through 1, it's been shifted across 4 units here. So now goes through at 4, 1. Or if we get rid of that, now we put on the 2 to the power x plus 4. Plus 4 is take away minus 4, so it's going to be shifted left. There we go, it's shifted left, and you can tell that this point here is this point shifted that way 4 units. Okay, next up I'm going to be talking about dilations. And once again, there's 2 types. There's the basic type that we're used to thinking about, which is when we might have y equals some number, capital A, times our a to the power x. And what it's going to do is, suppose here's our sort of original graph, if you like. It's going to take a point here and bring it either up or down, depending on what A is. So if A is 2, it's going to double it in this direction, or if A is half, it's going to halve it and bring it down. And our other one is when our graph might look like this, a to the power bx, and this is a dilation in the other direction. So supposing here's our original, it's going to take a random point and it's going to move it one of these ways, depending on what b is. Now, my preferred way for this type, this second type, my preferred way to deal with these is actually to realize that you can change it from y equals a to the power bx. You can change that to a to the power b all to the power of x. And so that'll just change your base, and you won't actually have to think about this, because this is just the same behavior as if you had a different base. Like, remember those graphs where we had 2 to the power x compared to 3 to the power x compared to 4 to the power x? That's kind of like all this was doing here. So, there you go, that's the dilation going on there. And to express the dilation, all you need to do is write a couple of coordinates for your points. Just write a few coordinates, some x, y coordinates. Even if you just write one, that's usually enough to show a dilation, unless you're sketching multiple graphs on the one set of axes. Now, a couple of extra points about reflections, translations, and dilations. And it's going to be about doing combinations of these things. So firstly, what happens if you do a combination of reflections? What happens if you've got y equals minus a to the power, sorry, this is a bit not very neat here, y equals minus a to the power negative x. So that's going, starting from here, it's doing a translation across the x-axis and across the y-axis. So what you're going to end up with, so the original was like this, then we flipped it one way, taking it to like this, and then we'll flip it in the other direction, taking it like that. So there's your final graph. Perhaps let me just draw it a bit more neatly here. It'll look more like that. Whoops, that. So there is 2 reflections happening at once. Now a few more points. Okay, I'm going to show you a few other important points through examples. So let's look at this example first. What if we have y equals half times 2 to the power x plus 1? Now, the question is here, how does this dilation work in with this translation? So the important thing to think about here, first, the translation definitely will sort of occur, if you like. So the best way to think about these translations is the translation will occur, so you can do those last if you've set it up properly. So first, let's consider about our dilation. We'll consider our dilation first. So our dilation will be taking it from 1, so our original graph sort of comes through here at this point of 1, and the asymptote is along y equals 0. But now it's going to be moving up or down a half, or by a factor of a half. So now it gets shifted. Instead of coming through a 1, it cuts through at a half. And just like this point here, when x is, say, when x is 1, it'll be a half times 2. So this point would have been, half times 2 would have been, oh, sorry, without thinking about the half, that would be 2. This point here, where it's 1, now that's half times 2, which is 1. So that point there is 1, 1 in this new graph. And now we can do the translation of up 1. So if we shift everything up 1, y. So if we shift everything up 1, the asymptote's here at 1. And this point cuts through now at 1.5, which is 3 on 2. Oops. There you go. And so this is our final graph. So another way to think about it, or yeah, like a common trap, perhaps. Here's a common trap that people might think about. They might go, okay, I've got a translation of 1, so move up 1. There we go. And so now I've got my date, and so translation of 1, and the graph should go through here at 2. So here's my graph. And then some people will accidentally go, oh, now I've got a dilation of a half. So this point, instead of being 2, will be half of a 2, and half of a 2 is 1. And they'll bring it back down, and they'll make like the normal graph, will get confused. But they forget that this translation means the asymptote must be where I've put it in, right there. Okay, so it must actually, this half only goes after this translation. So that will be there at 3 on 2, and it'll be shink, just like that. So if we change this this example a little bit to include the other sort of translation as well, so it was half 2x, say, minus 1 plus 1. So now we've also got a second translation. So just as before, first we do, so here's our graph of 2 to the power x, and it cuts through here at 1, and it's got another point here at 1, 2. So here we've done nothing. Here's our next graph. So we've got to remember to do our dilation first. So now we've got half of 2x, and it'll be, this is now a half, this is now 1, 1, is this point, and then we'll do our translations, x, y, and it doesn't matter which order we do our translations, so we can go up first if we like, and that's now 3 on 2, and this point here is now 1, we've gone up 1, so that's now 2, 1, 2 for that point. And now we're going to do this translation going to the right 1 unit, x, y, asymptote at 1. So now this point here where it cut through has been shifted across 1 unit. So this point here at 1, that point there is now the 1 and 3 on 2. So that's the point that used to be the y-intercept, and this other point that we had talked about is now shifted across at 2 and 2. So 2, 2. And now we have to find the new y-intercept as well. So we set x to 0, and so we've got y equals half 2 to the power 0 minus 1 plus 1. So that is half of 2 to the power minus 1 is 1 on 2 plus 1. So we've got a quarter plus 1. I'm going to write my 1 as 4 on 4, because now a quarter plus 4 quarters is 5 quarters. So this new intercept point here is 5 quarters. And that makes sense because that's a little bit higher than 1. So there we go. That's so we've learnt we need to do reflection. We've learnt we need to do dilations before translations. Okay, so we need to do dilations before translations. Okay, next thing we want to consider is what happens if we combine reflections and translations. what happens if we do that. So let's look at an example. Let's look at y equals 2 minus x plus 1. Okay, so here we've got a reflection in the y-axis, so it'll sort of flip this way around, and we've also got a translation here. And it looks, the way that it's written, it looks like it's going to be a translation that way, 1 unit. That's what it appears to be. So let's have a bit of a quick look at what this actually looks like by plotting it using a computer thing. Okay, so here we go, 2 to the power minus x plus 1, and here it is. So you can see this point where it cuts through 1 is here. It's actually been shifted to the right, not the left, and it has been also looking like it's been reflected as well. So from that we get that the general form actually is, this is the general form now, is that we need to put our negative sign, or our b, or our b, which could be a negative sign, and then x minus k. That's sort of our general form. So for this example we had here, we need to first factorize this negative sign out, and then write x minus 1, because we've got the negative factored out here. And now we've got to consider, do we need to do the reflection first or the translation first? Now let's consider those two things, and so we'll start off here. This can be a graph of y equals 2 to the power x, just looks like this, cuts through at 1. Now if we do the, let's start by doing the translation first. Okay, so we've moved across, so here is 1, 1 now, that's this point has shifted this way by 1 unit. And now if we were to do the reflection, what we're doing here is a reflection, if it's a reflection across the axes, then we run into trouble because this point jumps over to be over here if we're doing a reflection across the axes. Otherwise what we're doing is actually a reflection across this point, is across this, this point that we shifted. So the reflection would go that way, and that would give us the correct graph. Now, to avoid general confusion, if you've got it set up in this way, I would very, very much recommend doing the reflection first. And here's how that would be much easier. So here we've got y equals 2x, looks like that. Then if you do the reflection first, then we've got y equals 2 to the minus x, so it looks like that, and this is still the point 1. And then if we put in 2 to the minus, and we put in our translation now, so it's just been shifted this way, and that's much easier. This point becomes, instead of 0, 1, it becomes 1, 1, and it look like that. And we've still got to find this point, but you get the general idea. So from that, we can say do reflections. Do reflections before translations. Okay, so, and now I'm also going to, without trying to prove it to you, just say that it doesn't actually matter if you do dilations or reflections. Dilations and reflections, they can be done in either order, but my recommendation to you is to do dilations first. So let's get some extra space and just write order. So if it was me, I would do any dilations, then I would do reflections, and then I would do translations. Do that and you should be fine. Okay, so I'm going to finish off with this, finish this really long video with this really long question, I'm going to show you that it's actually pretty easy. So here it's sort of in standard form. We know that standard form is now big capital A for some sort of reflection and dilation times some number to the power b x minus k plus h. So here A and B are the terms that have reflections and dilations as part of them. Okay, so here's our question. And we notice that it's already in this form, but I like to get rid of this 2 because it can be a bit annoying. So we can use our index law to bring this 2 down. So it's 2 to the power of the 2, then minus x minus 3 plus 2, because now 2 squared is actually 4. So minus 2 times 4, which just makes life a little bit easier. X minus 3 plus 2. Now I'm going to, I notice that I've got here translation, another translation, a dilation, a reflection, another reflection, a dilation going on here with this 2, and 2 translations here. So I'm going to do my dilations first, then my reflections, then my translations. So to start me off, I'm just going to do a lopsided graph of 4 to the power x, just so that I know what my base graph looks like. And this point here is 1, and I'll track one other point as well. So let's track this other point just so you can see what happens. Track this point to be 1, so 4 to the power 1 is 4. Just so you can track what happens. Now originally this was a 2, so we've already done one dilation already by changing this base from 2 to 4. So we have done that dilation already, which is good. So now we've got our other dilations to do here. So now we're doing this 2 dilation, so we're changing it to 2 by 4 to the power x. So to incorporate this extra dilation here. So what that will do, instead of this cutting through 1, it will now cut through at 2. And this extra point will be now 1 and 8. Obviously this is a fairly poor picture. So there we go, that graph apparently will go through those. So that's our dilations. We've done the dilations. Now we're up to the reflections. So first I'll think about, I might do this reflection first. Doesn't really matter which order we do these 2 reflections. I'll do that one first, which goes across that way. So this one will, and my graph go that way. So it still cuts through at 2. But this point that used to be 1, 8 will now change to be over here. This 1 has been reflected, so it's now negative 1, 8. Okay, so now I'm going to do the other reflection, this one here, which is going to reflect this way. And I'll just do that on the same axis because it won't interfere. So it reflects along this axis here, the x-axis. I'll do this sort of thing. So now, instead of this being 2, it'll cut through at negative 2. And this point here, instead of this 8 being 8, it's been reflected. So this point is now negative 1, negative 8. There we go, negative 1, negative 8. So those are our 2 reflections done. Now all we've got to do are the 2 translations. So 2 translations, let's look at them. I'm going up 2 units, up 2, and I'm going to the right 3 units. So here on all my coordinates, this is like the x coordinate. This is sort of what's happening in the x coordinate. This is what's happening in the y coordinate. So we're doing a plus 3 in the x and a plus 2 in the y. In other words, whatever the coordinates are, for the x coordinate I'm doing plus 3 to whatever that one was, and to this y one I'm doing a plus 2 to whatever the y coordinate was. So let's have a look at those 2 things. So first I'll do the up bit. So if we go up, and we're going up 2, so instead of the asymptote being along the x-axis, the asymptote now is here at 2. So asymptote, and the graph will look basically the same. let me just yeah. Okay, so let's have a look at these points. So this point at -2, it's been lifted up 2 spots, so it goes through 0. This point here has been lifted up 2, so it's at -1. Instead of -8, it's now at -6. Okay, so now we'll do the translation in the x-coordinate. So this is the last thing we do, so I'm going to just make this one a little bit larger. 2. So what's going to happen is we're adding 3 to the coordinates, so the graph's shifted this way 3, so it'll look something a bit more like that. This one here. So here this point's shifted across 3 from 0, 0. It's now at 3, 0. And this point here that was at -1, -6 is now at +1, or +2 I should say. It's at +2 and -6 for this random point that we've been tracking the whole way through this process. And we also, so we've got this intercept here, which is kind of convenient for us that we've already got that one. Now we can find this one. It's the y-intercept, so we have to set x to being 0. Let's get a little bit more space here. So I'm using this equation. I'm setting x to being 0 to find the y-coordinate. So I've got y equals -2 by 4 to the power -x minus 3 plus 2. So x is 0 here, so it's a 0. So I'll put, so I've got y equals -2, 4, this is 4 to the power of a minus times a minus is positive, so it's -2 times 4 to the power of 3 plus 2. 4 to the power of 3 is, so 4 to the power of 3, 4 times 4, that's 16, times another 4, that is 64. Check that on your calculator if you like. So it's -2 times 64 plus 2, which then equals -128 plus 2, -126. So this point here where it cuts through is -126, and we've done everything. And we can double check. Yes, we've done this reflection. We've done that dilation. Yes, 4. We've got plenty of points that show that how dilated it is. Then we've done this reflection. Yes, we've done that translation, and we've done that translation. We've done everything. We've shown the asymptote. If we really want to, we can write the equation, y equals 2. That's the equation of the asymptote. Labelled our axes, drawn the graph in the right orientation, and labelled both of the axes intercepts. So we are fully finished. Very well done for sticking with this video right until the end, and I'll see you in class.